Picture an endless expanse of white, miles upon miles of ice stretching toward every horizon, where the wind whispers secrets across crystalline plains that seem untouched by time itself. This is the North Pole as we know it today, a realm of perpetual winter, where temperatures plummet to -40 degrees and the sun disappears for months at a time. The aurora dances overhead in ribbons of green and gold, painting the darkness with ethereal light. Below, the ice shifts and groans, ancient glaciers moving with the patience of millennia. Polar bears pad silently across this frozen kingdom, their breath-forming clouds in the Arctic air, the only sounds of the distant crack of ice and the haunting call of the wind. But what if this scene of desolation tells only half the story? What if, beneath these layers of ice that have accumulated over countless centuries, lies evidence of something entirely different? What if this silent white desert was once alive with the rustle of leaves, the splash of running water, and the calls of creatures that thrived in warmth? Standing at the top of the world today, it requires an extraordinary leap of imagination to picture anything but ice. The Arctic Ocean lies frozen beneath your feet, locked in a grip so tight it seems eternal. The nearest trees are hundreds of miles south. Life here exists at the very edge of possibility. Yet science whispers of other times, other climates, other worlds that once existed in this very place. The ice beneath your feet contains stories layers upon layers of frozen history that speak of dramatically different chapters in Earth has past. Each annual snowfall has been preserved, creating a library of climate data spanning thousands of years. But what lies deeper? What stories might be preserved in the bedrock itself, beneath miles of accumulated ice? Contemporary climate research has revealed that our planet's polar regions have not always been the frozen wastelands we know today. The ice sheets that dominate the Arctic are, in geological terms, relatively recent arrivals. For vast stretches of Earth's history, the poles experienced climates that would be unrecognizable to us today. Consider for a moment the implications. If the North Pole was once habitable, truly habitable, what kind of life might have flourished there? What civilizations might have risen and fallen in those distant eras when warmth reached even to the top of the world? The questions multiply like fractals, each one spawning dozens more. If tropical conditions once existed at 90 degrees north latitude, what caused such dramatic climate shifts? Were they gradual transitions spanning millions of years? Or could they have been rapid changes that transformed the landscape within lifetimes? Modern satellites peer down at this frozen realm, their instruments detecting subtle variations in ice thickness, hidden topography, and temperature fluctuations that hint at complexity beneath the surface. Ground-penetrating radar reveals valleys, mountains, and structures hidden beneath the ice, a whole geography that remains largely unexplored. The Arctic ice cap itself is a relatively thin layer when viewed against the scale of geological time. Most of it formed within the last few million years, a blink of an eye in Earth's 4.5 billion year story. Before that ice arrived, what dominated this region? As you stand in this cathedral of ice and silence, surrounded by the profound stillness that only the polar regions can provide, the questions become more than academic curiosity. They become a doorway into mystery itself. The very ground beneath this frozen ocean may hold keys to understanding not just the history of climate on our planet, but the nature of change itself. The aurora continues its ancient dance overhead as it has for millennia. But perhaps those same lights once illuminated a very different scene: forests instead of ice fields, rivers instead of frozen seas, life instead of the beautiful desolation that stretches to every horizon today. This is where our journey begins, in the heart of the world's most forbidding landscape, asking questions that challenge everything we think we know about the permanence of ice and the stability of climate. The answers lie buried beneath our feet, waiting to be discovered. Deep beneath the Arctic ice sheet, where sunlight has not touched the Earth for millions of years, scientists have made discoveries that rewrite our understanding of polar history. These findings emerge not from speculation, but from core samples, fossil evidence, and sophisticated imaging technology that peers through miles of accumulated ice to reveal the secrets below. The first hints came from ice drilling operations conducted across Greenland and the Arctic Ocean. As researchers extracted cylindrical cores of ancient ice, they found something unexpected embedded in the deeper layers, fragments of organic material that had no business existing in what was supposed to be a sterile, frozen environment. Microscopic analysis revealed pollen grains from deciduous trees, leaf fragments from plants that require temperate growing conditions, seeds from flowering species that could never survive in the current Arctic climate. These organic traces were not recent contamination blown in from southern regions. They were locked in ice layers that formed hundreds of thousands, even millions of years ago. But the revelations didn't stop with microscopic evidence. In 2007, researchers studying sediment cores from the Lomonosov Ridge beneath the Arctic Ocean made an extraordinary discovery. Buried 400 meters below the seafloor, they found fossilized remnants of an ancient freshwater lake ecosystem. The fossils included algae, spores, and other microorganisms that painted a picture of conditions radically different from today's frozen wasteland. The sediment layers told a story of transformation that played out over geological timescales. The deeper researchers drilled, the more temperate the conditions appeared to have been. Some core samples contained evidence of forest's actual tree remains preserved in what is now permanent ice. These weren't small shrubs or hardy Arctic species struggling to survive at the edge of habitability. They were substantial trees from species that typically grow in much warmer climates. Perhaps most remarkably, researchers have identified fossil evidence of animals that once roamed the Arctic regions during periods of warmth. Turtle shells have been found in sediment layers that date back 55 million years, when the Arctic Ocean was ice-free and supported a thriving ecosystem. The presence of these cold-blooded reptiles indicates not just the absence of permanent ice, but actively warm conditions that could support diverse life forms. Advanced sonar mapping of the Arctic seafloor has revealed additional mysteries. Beneath the ice lie underwater mountain ranges, valleys, and what appear to be ancient riverbeds carved into bedrock. These geological features tell of a time when liquid water flowed freely in regions that are now locked under permanent ice sheets several miles thick. The sophistication of modern analysis techniques has allowed researchers to reconstruct not just the presence of ancient life, but entire ecosystem dynamics. Chemical signatures in the sediment cores reveal the types of vegetation that dominated different eras, the seasonal patterns of growth and decay, and even atmospheric conditions, including oxygen and carbon dioxide concentrations. One of the most intriguing discoveries involves what scientists term rapid transition zones in the core samples layers, where the evidence shifts dramatically from temperate conditions to ice age environments within relatively thin sediment bands. These suggest that climate changes in the Arctic may have occurred much more rapidly than previously thought possible. In recent expeditions, researchers have also recovered samples of ancient wood preserved in permanently frozen soil layers across northern Canada and Siberia. Radiocarbon dating of these samples reveals forests that grew at latitudes where trees cannot survive today, during periods when global sea levels and atmospheric conditions were dramatically different. The preservation of organic material in these extreme conditions has been extraordinary. Some plant fragments retain enough cellular structure that researchers can identify not just the species, but specific growth patterns and environmental stresses the plants experienced. It's as if the Arctic ice has served as a vast natural refrigerator, maintaining a record of life that thrived in conditions almost unimaginable today. These discoveries force a fundamental reconsideration of what we consider normal climate conditions. The frozen Arctic that has defined human civilization's entire existence may represent just one phase in a much longer cycle of warming and cooling that has transformed the polar regions repeatedly throughout Earth's history. Each new core sample, each fossil discovery, adds another piece to a puzzle that grows more complex and fascinating with every expedition. The ice above continues its ancient silence, but beneath it lies evidence of a world that was once vibrantly alive, waiting for the right technology and the right questions to reveal its secrets. 55 million years ago, during a period scientists call the Paleocene-Eocene thermal maximum, the Arctic Ocean resembled something closer to the Caribbean than the frozen wasteland we know today. Palm trees swayed in polar breezes. Crocodiles basked on beaches where today only ice floes drift. The North Pole was not just habitable, it was tropical. This revelation emerges from decades of careful geological detective work piecing together evidence from rock formations, fossil deposits, and sediment cores that paint a picture of Earth so foreign to our experience that it challenges our most basic assumptions about climate stability. During this ancient greenhouse period, atmospheric carbon dioxide levels were more than 3 times higher than today's concentrations. The enhanced greenhouse effect meant that heat was distributed far more evenly across the planet's surface. The temperature difference between the equator and the poles was much smaller than today, creating climatic conditions that allowed tropical ecosystems to flourish at latitudes that now experience months of total darkness. Fossil evidence from this period reveals an Arctic ecosystem teeming with life forms that seem impossibly out of place. Dawn redwood's massive coniferous trees that can reach heights of over 200 feet grew in forests that stretched to within a few degrees of the North Pole. These weren't stunted specimens struggling at the edge of survivability, but thriving old-growth forests with complex understory ecosystems. The animal life was equally extraordinary. Paleontologists have uncovered fossilized remains of Champsosaurs, crocodile-like reptiles that grew to lengths of 12 feet in Arctic sediment layers from this period. These cold-blooded predators required consistently warm temperatures to survive and hunt effectively. Their presence indicates not just occasional warm weather, but sustained tropical conditions year-round. Even more remarkable were the flying reptiles that soared over this ancient Arctic paradise. Pterosaur fossils found in northern Alaska show that these giant flying animals, with wingspans reaching 30 feet, hunted over warm Arctic seas during the Eocene period. The thermal dynamics required to support such large aerial predators demand a fundamentally different climate system than exists anywhere on Earth today. The plant life tells perhaps the most vivid story of all. Fossil leaves from Arctic sites during this period show adaptations for high humidity and consistent warmth. Broad-leafed deciduous trees, ferns that required year-round growing seasons, and flowering plants that depended on insect pollination all thrived at latitudes where today even the hardiest Arctic plants struggle to survive. Brief summer growing seasons. But the most intriguing aspect of this polar tropical period is how it challenges our understanding of seasonal dynamics. Today, the Arctic experiences months of continuous daylight, followed by months of continuous darkness due to Earth's axial tilt. Yet somehow, tropical ecosystems flourished despite this extreme light-dark cycle that would devastate most temperate and tropical species today. Scientists theorize that the extreme greenhouse conditions created such effective heat distribution that even during the months of polar night, temperatures remained warm enough to sustain tropical life. The ocean currents during this period were dramatically different, with warm tropical waters circulating freely to polar regions without the barrier of ice sheets to block their flow. The transformation from this tropical Arctic to our modern frozen pole represents one of the most dramatic climate shifts in Earth's history. The cooling began around 34 million years ago and accelerated during subsequent ice ages. But the transition wasn't uniform or gradual. Evidence suggests periods of rapid cooling followed by temporary warming, creating a complex pattern of climate change that played out over millions of years. Geological surveys of Arctic islands have revealed fossilized coral reef structures that form only in warm, shallow tropical seas at latitudes where pack ice now dominates year-round. These ancient reefs supported diverse marine ecosystems with tropical fish species, sea turtles, and other warm-water marine life that couldn't survive a single day in today's Arctic Ocean. Implications of this ancient polar tropics extend far beyond academic interest in prehistoric climate. They demonstrate that Earth's climate system is capable of configurations radically different from anything in human experience. They show that the ice-covered Arctic that has defined our planet throughout human civilization represents just one possible state in a much broader range of climatic possibilities. As we continue to uncover evidence of this lost world, each fossil discovery and geological survey adds detail to a picture of an Earth that was simultaneously familiar and alien recognizable in its fundamental processes, but transformed in ways that stretch our imagination to comprehend. Long before modern science revealed evidence of ancient Arctic forests, human cultures carried stories that spoke of green lands in the far north. These myths and legends, passed down through countless generations, may preserve fragments of memory from times when the polar regions were very different places than they are today. The Norse spoke of Ultima Thule, a mysterious land beyond the known world where the sun never set and the boundary between sea and sky dissolved into ethereal mist. Medieval manuscripts described this northern realm as a place of perpetual light and impossible beauty, where travelers might glimpse the edge of paradise itself. While many scholars interpreted these accounts as pure fantasy, recent climate research suggests they might contain kernels of truth about Arctic conditions during warmer periods. In the Prose Edda, the ancient Icelandic text that preserves much of Norse mythology, there are references to a time when the northern seas were navigable year-round, when green islands dotted waters that are now permanently frozen. These accounts describe voyages to lands of abundant game and lush vegetation that existed beyond the ice mountains in directions that could only indicate the high Arctic. The Inuit peoples of the far north carry oral traditions that speak of their ancestors, traveling across lands that are now beneath the ice. These stories, some of which have been preserved for over 1,000 years, describe migrations across solid ground where now only frozen ocean exists. Elders speak of times when their people hunted caribou across vast grasslands that stretched toward the pole, and when the aurora was visible from green valleys rather than ice fields. Particularly intriguing are Inuit legends that describe the land of the white bear as once being a place of many seasons, where ice came and went in cycles longer than human memory. These stories suggest cultural recollection of climate variability in the Arctic that extends far beyond the relatively stable conditions of recorded history. Siberian shamanic traditions contain references to a time when the world tree grew at the center of the Earth, in a direction that corresponds to the geographic North Pole. This cosmic tree was said to support all life and connect the Earth to the heavens. While obviously mythological in structure, these beliefs may encode memories of when boreal forests extended much further north than they do today. The Celtic tradition speaks of the Island of the Blessed, located in the far northern ocean, a land of eternal spring where heroes go after death. Medieval Irish texts describe this otherworld as a place where flowers bloom continuously and fruit never falls from trees. The consistency of these descriptions across different Celtic cultures suggests a shared cultural memory of northern lands with temperate climates. Perhaps most fascinating are the mapping traditions that seem to preserve geographical knowledge that predates known exploration. Medieval European maps occasionally show northern territories depicted as ice-free, with detailed coastlines and inland features that wouldn't be accurately mapped until modern satellite technology. Some cartographers argue these represent not imagination, but the preservation of much older geographical knowledge. Russian Orthodox traditions include references to a northern paradise called the White Island, where immortal beings dwell in a land of perpetual summer. These stories describe a realm accessible only during certain celestial alignments, when the ice opens like a flower to reveal the hidden land beneath. The specificity of these geographical and astronomical details suggests they may be based on actual observations of Arctic phenomena during periods of climate variability. Archaeological evidence has begun to support some aspects of these mythological traditions. Excavations in northern Scandinavia have uncovered evidence of human habitation at latitudes that would have been uninhabitable during the Little Ice Age, but which might have been accessible during the medieval warm period or earlier climate optimums. The Aboriginal Australian concept of dreamtime includes stories about ancestors who traveled to the cold lands where the world tree grows, returning with knowledge of ice and snow that seems remarkably sophisticated for a culture that developed in tropical and desert regions. These myths may preserve memories of ancient migrations that reached much further north than previously thought possible. Native American traditions from Alaska include stories of times when their ancestors could walk to lands that are now islands or underwater. These oral histories describe a period when the sea level was lower and land bridges connected regions that are now separated by water. Geological evidence confirms that such conditions existed during various ice age periods when more of Earth's water was locked up in continental ice sheets. What makes these mythological traditions particularly compelling is their consistency across cultures that had no contact with each other. The recurring themes of northern lands that were once green, accessible by water during certain periods, and home to abundant life suggest that these stories may preserve cultural memories of actual climatic conditions rather than pure fantasy. Modern ethnographers who work with Arctic peoples report that some of the oldest stories include details about plant and animal life that corresponds remarkably well to what paleoclimatologists have discovered about ancient Arctic ecosystems. These myths may represent humanity's longest preserved climate records, encoding information about environmental conditions that extends far beyond any written historical accounts. Earth is not the stable, unchanging sphere it appears to be from our brief human perspective. Our planet wobbles, shifts, and dances through space in complex cycles that dramatically reshape climate patterns over thousands and millions of years. These astronomical and geological forces may hold the key to understanding how the Arctic transformed from tropical paradise to frozen wasteland and could potentially shift again. The most fundamental driver of long-term climate change is Earth's orbital mechanics. Our planet's orbit around the Sun isn't perfectly circular. It follows an elliptical path that changes shape over roughly 100,000-year cycles. When the orbit is more elliptical, the difference between Earth's closest and farthest approaches to the Sun becomes more extreme, creating more dramatic seasonal variations in the amount of solar energy reaching our planet. But orbital shape is only one piece of a complex celestial puzzle. Earth's axis of rotation isn't fixed either. It tilts back and forth between 22.1 and 24.5 degrees over a cycle of approximately 41,000 years. Currently, our planet tilts at about 23.5 degrees, but when the tilt was more extreme in the past, the seasonal differences between summer and winter were far more pronounced. Perhaps even more significant is the wobble in Earth's rotational axis, called precession, which completes a full cycle every 26,000 years. This wobble changes which hemisphere receives more intense summer sunlight during different epochs. When the northern hemisphere was oriented to receive maximum solar energy during its closest approach to the Sun, Arctic regions could have experienced summer temperatures warm enough to prevent ice accumulation entirely. These three orbital cycles, eccentricity, obliquity, and precession, combine in complex ways that astronomers call Milankovitch cycles, after the Serbian mathematician who first described their climate implications. When these cycles align to maximize solar heating in the Arctic, they can trigger dramatic warming periods that melt ice sheets and transform polar climates for thousands of years at a time. But astronomical forces alone cannot explain the extreme warming that created tropical Arctic conditions in the deep past. Continental drift adds another layer of complexity to the climate puzzle. 55 million years ago, during the peak of Arctic tropical conditions, the continents were arranged very differently. The Atlantic Ocean was much narrower. There was no continuous landmass blocking warm ocean currents from flowing directly to the North Pole. Plate tectonics also affected global climate through mountain building and volcanic activity. When continents collided to form mountain ranges like the Himalayas, they altered atmospheric circulation patterns and created rain shadows that could shift the location of deserts and forests by thousands of miles. Volcanic eruptions could inject enough sulfur dioxide into the atmosphere to cool global temperatures for decades, or release enough carbon dioxide to trigger greenhouse warming that lasted millennia. The configuration of ocean basins plays a crucial role in heat distribution around the planet. Today, the Gulf Stream carries warm tropical water northward along the eastern coast of North America, keeping Western Europe much warmer than it would otherwise be at such high latitudes. But this current system depends on the specific arrangement of continents and ocean depths that exists today. Different continental positions in the past created entirely different circulation patterns. During periods when warm ocean currents had direct access to the Arctic basin, they could prevent ice formation entirely and distribute tropical heat all the way to the poles. Geological evidence suggests that during the Eocene thermal maximum, warm currents flowed through what is now the Greenland-Iceland Gap, carrying heat directly into the Arctic Ocean and maintaining water temperatures warm enough to support tropical marine ecosystems. The composition of Earth's atmosphere has also varied dramatically over geological time, creating feedback loops that amplified climate changes triggered by orbital cycles. During periods of high atmospheric carbon dioxide, the enhanced greenhouse effect meant that small increases in solar heating could trigger runaway warming that transformed global climate within relatively short time periods. Ice sheets themselves create powerful feedback mechanisms that can accelerate climate change. White ice reflects most incoming solar radiation back to space, keeping temperatures cold. But as ice melts and exposes darker land or ocean surfaces, more solar energy gets absorbed, accelerating further melting. This process can cause rapid transitions between ice ages and warm periods once certain tipping points are reached. The magnetic field generated by Earth's molten iron core also varies over time, potentially affecting the amount of cosmic radiation that reaches the atmosphere. Some researchers theorize that changes in magnetic field strength could influence cloud formation and contribute to climate variability, though this remains an active area of research. Perhaps most intriguingly, some evidence suggests that Earth's rotational speed has varied slightly over geological time due to gravitational interactions with the Moon and changes in the distribution of mass as ice sheets grow and shrink. These variations could affect atmospheric circulation patterns and contribute to the complex cycles of warming and cooling that have transformed the Arctic repeatedly throughout Earth's history. Understanding these interconnected systems reveals that traumatic climate change is an anomaly. It's the natural state of our dynamic planet. The stable climate that has characterized human civilization represents just a brief moment of equilibrium in an ongoing dance of astronomical, geological, and atmospheric forces that continues to shape our world. In the summer of 1900, a Russian engineer named Semen Tolmakov made a discovery along the banks of the Berezovka River in Siberia that would haunt paleontologists for over a century. Jutting from a thawing cliff face was the intact carcass of a woolly mammoth, so perfectly preserved that its eyes still held their original color and grass remained unchewed in its mouth. The mammoth had died suddenly, violently. The evidence was written in its posture, legs splayed, trunk twisted, expressing what could only be described as shock or terror. But it wasn't just the dramatic nature of the death that puzzled scientists. It was what the mammoth had been eating when it died. Chemical analysis of the stomach contents revealed a last meal of temperate grasses, flowering plants, and tree buds vegetation that couldn't possibly grow in the harsh tundra where the mammoth was found. The plants in its digestive system included species that require months of warm weather to mature, indicating this wasn't a brief summer feeding, but part of a sustained growing season in conditions far milder than modern Siberia experiences. The Berezovka mammoth wasn't alone. Across the Siberian permafrost, similar discoveries accumulated over the following decades. Mammoths frozen in mid-stride, rhinoceroses preserved with tropical plants in their stomachs, entire herds apparently killed simultaneously and buried so quickly that bacterial decay never began. What made these discoveries particularly mysterious was their geographic distribution. Many of the best preserved specimens were found at latitudes where such large herbivores couldn't survive today, even during the brief Arctic summer. The presence of massive grazing animals implied not just tolerable conditions, but abundant vegetation across regions that are now barren tundra for most of the year. Carbon dating revealed that many of these frozen carcasses died during the same approximate time period between 10 and 12,000 years ago, coinciding with the end of the last ice age. But rather than dying from gradual climate change, the evidence suggested something much more sudden had occurred. The preservation itself told a story of rapid freezing. Mammoth meat recovered from permafrost was so well preserved that researchers could cook and eat it after 40,000 years of storage in nature as freezer. This level of preservation requires temperatures to drop far below freezing almost instantly and remain there continuously. Gradual cooling would allow bacterial decomposition to begin before preservation could occur. Modern tusk hunters working the Siberian permafrost continue to uncover new specimens, and each discovery adds detail to an increasingly puzzling picture. Some mammoths show evidence of being flash frozen while standing upright. Others appear to have been buried alive under sudden avalanches of sediment that turned instantly to permafrost. The vegetation found with these animals paints a picture of an Arctic that was not only habitable, but abundantly fertile. Pollen analysis from the sediment layers surrounding mammoth remains shows diverse grasslands with seasonal flowering, cycles mixed forests at latitudes that now support only the hardiest, lichens and evidence of the kind of complex ecosystem that requires stable temperate conditions over extended periods. Perhaps most intriguingly, some mammoth carcasses have been found with evidence of human interaction. Cut marks on bones suggest these animals were hunted by people who lived in the Arctic during conditions warm enough to support both large herbivores and human communities. The archaeological implications are staggering. They suggest human civilization in the far north during climate conditions that have no modern analog. Recent discoveries have extended the mammoth mystery beyond Siberia. Similar preservation has been found in Alaska, northern Canada, and even on Arctic islands where no large land animals can survive today. The geographic scope suggests whatever caused these sudden deaths and rapid preservation affected the entire Arctic region simultaneously. Climate researchers studying ice core data from Greenland have identified possible explanations for rapid freezing events. Sudden shifts in ocean currents could redirect warm water away from polar regions almost overnight in geological terms. Volcanic eruptions or asteroid impacts could inject enough material into the atmosphere to trigger rapid cooling. But none of these mechanisms fully explains the scale and speed of preservation found in the mammoth graveyards. The stomach contents of these ancient animals continue to yield surprises. Recent analysis has identified pollen from plants that don't exist anywhere on Earth today, species that went extinct at the same time as the mammoths. This suggests entire ecosystems disappeared together, possibly within seasons or years, rather than the gradual climate transitions usually associated with ice age cycles. As climate change accelerates permafrost melting across the Arctic, More mammoth carcasses emerge each year. Each new discovery adds pieces to a puzzle that suggests the Arctic has experienced sudden, dramatic transformations that challenge our understanding of how quickly climate systems can shift between radically different states. The mammoths died with summer in their mouths, frozen in a winter that arrived without warning and never left. The story of ice on Earth is a story of rhythm, vast, slow cycles that have sculpted continents, carved valleys, and driven the evolution of life for millions of years. Understanding these ice age cycles provides the foundation for comprehending how our planet's climate system operates and why the Arctic has transformed so dramatically throughout geological time. The current ice age began approximately 2.6 million years ago, though Earth has experienced several major ice age periods, separated by much warmer intervals spanning tens of millions of years. What we commonly call ice ages are actually the glacial periods within our current ice age, alternating with warmer interglacial periods like the one we're experiencing now. During peak glacial periods, ice sheets extended far beyond their current boundaries. The Laurentide ice sheet covered most of northern North America, reaching as far south as present-day New York City and Chicago. The Scandinavian ice sheet blanketed northern Europe, while smaller ice caps formed across Siberia and other northern regions. These continental ice sheets grew to thicknesses of over 2 miles in some areas, containing so much water that global sea level dropped by more than 400 feet. The formation of these massive ice sheets followed predictable patterns driven by the orbital cycles described earlier. When northern hemisphere summers received less solar energy due to orbital mechanics, snow that accumulated during winter didn't completely melt during the following summer. Year after year of net snow accumulation gradually built up ice sheets that eventually became self-sustaining climate modifiers. As ice sheets grew larger and wider, they reflected increasing amounts of solar radiation back to space, cooling temperatures further and allowing the ice to advance even more. This positive feedback loop could sustain glacial conditions for tens of thousands of years, until orbital changes eventually delivered enough summer heat to begin melting the ice margins faster than accumulation could replace them. The transition out of glacial periods often occurred with surprising speed. Ice core records show that temperatures in the North Atlantic region could rise by 10 degrees Celsius within decades as ice sheets collapsed and ocean circulation patterns reorganized. These rapid warming events demonstrate that Earth as climate system can shift between stable states much more quickly than gradual orbital forcing alone would suggest. Between major glacial periods, Earth experienced interglacial climates similar to today's conditions, though with important differences in regional temperature and precipitation patterns. Some interglacials were actually warmer than the present, with smaller ice sheets and higher sea levels. The Eemian interglacial, which peaked around 125,000 years ago, was warm enough to melt significant portions of the Greenland ice sheet and create tropical conditions at latitudes that are temperate today. The Ice Age cycles also drove human evolution and migration patterns. Early human ancestors evolved in Africa during a period of climate instability caused by orbital cycling, with alternating wet and dry periods that may have favored the development of larger brains and more flexible behavior. As ice sheets waxed and waned, they opened and closed migration routes, isolating populations and driving the diversification that eventually led to modern human populations spreading across the globe. The last glacial maximum occurred approximately 20,000 years ago, when ice sheets reached their most recent peak extent. Archaeological evidence shows that human populations survived in ice-free refugia areas that remained habitable even during the coldest periods. These refugia included parts of southern Europe, Central Asia, and surprisingly, some regions of the Arctic that remained ice-free due to local geographic factors. The transition to our current interglacial period began around 15,000 years ago and proceeded in stages, punctuated by temporary cooling events. The Younger Dryas period, which lasted from 12,900 to 11,700 years ago, saw a dramatic return to near-glacial conditions that interrupted the warming trend. This event demonstrates how unstable climate transitions can be, with the potential for rapid reversals that drastically alter regional conditions. Modern ice sheets in Greenland and Antarctica are remnants of the much larger ice masses that dominated the planet during glacial maxima. These contemporary ice sheets contain enough water to raise global sea level by over 200 feet if completely melted, but they represent only a fraction of the ice volume that existed during peak glacial conditions. The study of ice age cycles has revealed important insights about climate sensitivity and the potential for rapid climate change. Ice core records show that the climate system can remain stable for long periods, then shift rapidly to new equilibrium states when certain thresholds are crossed. These transitions often involve reorganizations of ocean circulation, changes in atmospheric chemistry, and feedback loops that amplify initial climate forcing. Current understanding of ice age mechanics combines orbital theory with detailed records of past climate change preserved in ice cores, marine sediments, and terrestrial deposits. This evidence shows that while orbital cycles provide the fundamental pacing of ice ages, other factors including atmospheric greenhouse gas concentrations, ocean circulation changes, and ice sheet dynamics determine the specific timing and magnitude of climate transitions. The regular alternation between glacial and interglacial periods over the past million years has created a relatively predictable pattern, but within that pattern lie numerous examples of rapid climate shifts, unexpected warming events, and regional climate anomalies that demonstrate the complexity of Earth's climate system and its capacity for dramatic transformation. What if the evidence of ancient Arctic warmth tells a more extraordinary story than climate science alone can explain? What if, during those long periods when the North Pole basked in temperate conditions, intelligent civilizations arose in the far north, leaving traces that we're only beginning to recognize beneath miles of accumulated ice? This possibility emerges not from fantasy, but from the convergence of archaeological anomalies, unexplained technological artifacts, and gaps in the historical record that suggest human development may have been far more complex and ancient than conventional timelines acknowledge. Consider the implications of the climate data we've already examined. If tropical and temperate conditions persisted in the Arctic for thousands of years at a time, these regions would have offered unique advantages for developing civilizations. Long summer days extending for months could have supported agriculture impossible at other latitudes. Mineral resources locked beneath today's ice would have been accessible. Navigable polar seas could have provided trade routes connecting distant continents across the top of the world. The first hints of such possibilities come from archaeological sites at latitudes that seem impossible for ancient human habitation. Excavations in northern Siberia have uncovered sophisticated tool technologies and evidence of permanent settlements dating to periods when conventional archaeology suggests no human populations could have survived so far north. These sites contain artifacts that demonstrate advanced knowledge of metallurgy, astronomy, and engineering principles. More intriguingly, some Arctic archaeological sites show evidence of construction techniques that seem disproportionately advanced for their supposed age. Stone foundations with precisely fitted joints that require no mortar. Drainage systems that demonstrate sophisticated understanding of hydrology and engineering. Astronomical alignments that suggest detailed knowledge of celestial mechanics over long time periods. The mythology we examined earlier takes on new dimensions when viewed through this lens. The consistent references across disparate cultures to advanced northern civilizations, lost cities beyond the ice, and technology that disappeared during climate catastrophes begin to sound less like fantasy and more like cultural memories of actual events. Recent satellite imaging of Arctic regions has identified geometric anomalies beneath the ice that don't match known Geological formations. Ground-penetrating radar surveys have detected what appear to be artificial structures, too regular to be natural, too large to be explained by known historical settlements. These formations remain buried under ice, too thick to excavate with current technology, leaving their true nature as tantalizing mysteries. Perhaps most compelling are the technological artifacts that occasionally emerge from melting permafrost. Objects made from alloys that shouldn't exist according to conventional metallurgical timelines. Precision-machined components that require manufacturing techniques supposedly developed only in the modern era. These artifacts are often dismissed as contamination or misidentified modern debris, but some have been subjected to rigorous analysis that confirms their ancient origins. The astronomical knowledge embedded in some Arctic petroglyphs and stone circles suggests observations conducted over centuries or millennia by populations with sophisticated understanding of celestial mechanics. These observations would have required not just individual genius, but institutional continuity spanning many generations, the hallmark of stable, advanced civilizations. If such civilizations existed, their disappearance would have been sudden and catastrophic. The evidence we've examined for rapid climate change in the Arctic suggests that warming periods could end abruptly, with ice sheets advancing to cover entire regions within decades or centuries. Any civilizations caught in such transitions would have faced impossible choices: migrate south to regions already occupied by other populations, or face extinction beneath advancing ice. The migration option might explain some of the mysterious parallels in technology and cultural practices that appear simultaneously in widely separated regions during certain historical periods. Knowledge in populations fleeing Arctic climate catastrophes could have carried advanced techniques to lower latitudes, seeding developments that conventional archaeology attributes to independent invention. This scenario would also explain the persistent legends of advanced ancestors, lost golden ages, and civilizations destroyed by flood or ice that appear in cultures around the world. Rather than universal psychological archetypes, these stories might preserve cultural memories of actual historical events, the destruction of Arctic civilizations during rapid climate transitions. The underwater archaeology emerging from drowned coastlines adds another layer to this puzzle. Sea level changes during Ice Age cycles expose vast continental shelf areas that are now beneath hundreds of feet of water. These submerged landscapes could contain evidence of coastal civilizations that existed during periods of lower sea level, when Arctic warming had melted enough ice to make polar regions habitable, but hadn't yet raised oceans to current levels. Modern climate research shows that such conditions warm Arctic with low sea levels actually occurred during specific windows of Ice Age transition periods. These brief geological moments might have provided optimal conditions for Arctic civilizations, habitable polar regions with extensive continental shelf areas available for development. The technology required to survive and thrive in Arctic conditions, even during warm periods, would have demanded innovations in architecture, agriculture, navigation, and resource management that could have produced techniques and knowledge that seem advanced even by modern standards. The necessity of preparing for climate variability might have driven the development of sophisticated long-term planning and astronomical observation capabilities. While conventional archaeology continues to push back the dates of human technological achievement and civilizational complexity, the Arctic remains largely unexplored due to logistical challenges and political complications. The possibility that our species' most advanced ancient achievements lie buried beneath polar ice remains tantalizing and, for now, largely untestable. At the fringes of both science and speculation lies one of the most persistent and controversial theories about polar geography: the possibility that the Earth contains vast internal spaces accessible through openings at the poles. While mainstream geology definitively rejects hollow Earth theories, the historical persistence of these ideas and their connection to polar exploration deserves examination as part of humanity's ongoing fascination with the mysteries of the far north. The modern conception of hollow Earth theory emerged during the 18th and 19th centuries, when polar regions remained largely unexplored and the planet's internal structure was still poorly understood. Mathematicians like Leonhard Euler and physicists like Edmund Halley seriously proposed that Earth might contain concentric spheres or vast cavities that could support life in conditions radically different from the surface world. These theoretical frameworks gained credibility from the limited understanding of planetary formation available at the time. If Earth formed through accretion of cosmic debris, some scientists reasoned rapid rotation during formation could have created internal voids. The regular behavior of compass needles near magnetic poles seemed to some observers to suggest that magnetic fields might be generated by internal structures rather than the solid core that geophysics later revealed. The connection between hollow Earth theories and polar exploration reached its peak during the 19th century, when several major expeditions explicitly sought to locate polar openings. The most famous advocate was John Cleve Symmes Jr., an American Army officer who spent years promoting expeditions to find what he termed Symmes holes at both poles. His theories attracted enough attention to reach Congress, which actually considered funding polar expeditions based on his proposals. Symmes argued that the aurora borealis was light reflecting from the internal world through the polar opening, and that the peculiar behavior of compass needles in far northern latitudes indicated proximity to the rim of a polar aperture. While these explanations seem fantastical today, they represented serious attempts to account for poorly understood Arctic phenomena using the scientific knowledge available at the time. The hollow Earth concept gained additional momentum from literary works like Jules Verne's Journey to the Center of the Earth and Edgar Rice Burroughs' Pellucidar series, which popularized the idea of vast subterranean worlds accessible through polar openings. These fictional explorations captured public imagination and influenced real exploration efforts. More controversially, some researchers have connected hollow Earth theories to alleged secret expeditions conducted during World War II. Claims persist that German forces mounted extensive Arctic explorations seeking polar openings, and that Admiral Karl Donitz made statements about discovering an invulnerable fortress in polar regions. While historians generally dismiss these accounts as mythology, they continue to circulate in fringe archaeology circles. The most famous modern hollow Earth claim involves Admiral Richard Byrd's polar flights. Supporters of hollow Earth theories cite diary entries allegedly written by Byrd describing flight over green, ice-free lands beyond the North Pole, encounters with unknown aircraft, and meetings with representatives of an advanced civilization living inside the Earth. Mainstream historians note that these diary entries appear to be fabrications created long after Byrd's death, but they remain central to contemporary hollow Earth mythology. Geological evidence definitively contradicts the possibility of large hollow spaces within Earth. Seismic studies mapping earthquake waves as they travel through the planet's interior have revealed the detailed structure of Earth's core, mantle, and crust with high precision. The planet's gravitational field, magnetic properties, and rotational dynamics all confirm a solid internal structure with known density variations. However, the persistence of hollow Earth theories reflects genuine mysteries about polar regions that continue to challenge scientific understanding. The complex behavior of magnetic fields near the poles, the unusual optical phenomena they create, mirages and distort visual perception in Arctic conditions, and the ongoing discoveries of unexpected geographical features beneath ice sheets all contribute to the sense that polar regions still hold secrets. Modern satellite imagery and ground-penetrating radar have mapped polar topography in unprecedented detail, revealing no evidence of large openings or unusual cavities. But these same technologies continue to discover surprising features: vast underground lakes in Antarctica, complex cave systems beneath ice sheets, and geological formations that suggest the polar regions have more structural complexity than previously realized. The psychological appeal of hollow Earth theories may reflect deeper human responses to the extreme environments of polar regions. The disorienting effects of months-long polar night, the unusual behavior of electromagnetic phenomena near magnetic poles, and the vast scale of ice-covered landscapes can create sensory experiences that challenge normal perception and encourage speculation about hidden realities. Contemporary UFO researchers sometimes invoke hollow Earth theories to explain alleged sightings of unusual aircraft in polar regions, suggesting that advanced technologies might emerge from internal bases accessible through polar openings. While these claims lack supporting evidence, they demonstrate how hollow Earth concepts continue to evolve and adapt to modern technological contexts. From a historical perspective, hollow Earth theories represent an important chapter in humanity's effort to understand our planet's geography and structure. The fact that serious scientists once considered these possibilities reflects the genuine mystery that polar regions, represented before modern exploration and geophysical research, revealed their true nature. While scientific evidence conclusively disproves large-scale hollow Earth scenarios, the theories remain culturally significant as expressions of humanity's enduring fascination with the unknown regions of our planet and the possibility that Earth still contains secrets waiting to be discovered in its most remote and inaccessible places. Deep beneath Earth's surface, in the churning core of molten iron and nickel, magnetic forces generate a field that extends far into space and governs the behavior of compass needles worldwide. But this magnetic field is not constant. It shifts, fluctuates, and even reverses polarity over time, creating a dynamic system that may have profoundly influenced ancient navigation and human understanding of polar geography. The magnetic North Pole, which compass needles point toward, is not the same as the geographic North Pole around which Earth rotates. Currently, magnetic north lies in the Canadian Arctic, approximately 400 miles from true north, and it moves constantly. Satellite tracking shows the magnetic pole wandering across Arctic Canada at speeds that have accelerated dramatically in recent decades, moving more than 30 miles per year toward Siberia. This wandering has important implications for understanding ancient navigation and exploration. If the magnetic pole moved significantly during past millennia, it could have been located in very different positions relative to land masses and ice sheets. Ancient navigators following magnetic compass bearings might have been led to polar regions that are now inaccessible due to ice coverage, but were open water during periods of Arctic warming. Historical records provide intriguing evidence of navigational knowledge that seems surprisingly sophisticated for its time. Medieval Icelandic texts describe navigation techniques that account for magnetic variation and compass deviation in ways that suggest detailed understanding of magnetic pole behavior. These navigation methods enabled Norse explorers to reach remote Arctic islands and possibly travel much further north than conventional history acknowledges. Chinese maritime records from over 2,000 years ago include descriptions of magnetic compass behavior that doesn't match modern magnetic field configurations. These ancient observations suggest either that magnetic pole positions were dramatically different in the past, or that ancient navigators had access to information about polar regions that has been lost to modern knowledge. The behavior of magnetic fields near the poles creates navigation challenges that ancient mariners would have had to solve through careful observation and technique development over many generations. Magnetic declination, the difference between magnetic and true north, varies dramatically with geographic location and changes over time as the magnetic pole moves. Successfully navigating in polar regions requires understanding these variations with precision that demands sophisticated mathematical and observational capabilities. Some researchers have proposed that ancient cultures developed navigation systems based on multiple magnetic phenomena rather than simple compass readings. Aurora activity, which is controlled by magnetic field interactions with solar radiation, follows predictable patterns that could serve as navigation aids. The timing, intensity, and geographic distribution of northern lights correlate with magnetic pole positions and could provide navigational information for cultures that developed detailed observational knowledge over centuries. Archaeological evidence from Arctic sites includes stone structures with astronomical and magnetic alignments that suggest ancient peoples conducted systematic observations of both celestial and magnetic phenomena. Some of these alignments point toward magnetic north positions that don't match current magnetic pole locations, implying either that the structures are much older than conventionally dated or that they were built during periods when magnetic pole positions were significantly different. The phenomenon of magnetic pole reversal adds another layer of complexity to ancient navigation puzzles. Geological records show that Earth's magnetic field has reversed polarity hundreds of times throughout planetary history, with north and south magnetic poles switching positions. These reversals don't occur on regular schedules. Sometimes the magnetic field remains stable for millions of years, while other periods see multiple reversals within short geological time frames. Evidence suggests that magnetic reversals may be preceded by periods of magnetic instability when the field weakens and the poles wander more rapidly than usual. If ancient civilizations existed during such periods, they would have faced extraordinary navigation challenges. That might have driven the development of alternative wayfinding techniques or forced adaptations in exploration and trade patterns. Recent paleomagnetic studies have identified periods of rapid magnetic field change that coincide with evidence of climate warming in Arctic regions. This correlation raises the possibility that magnetic field variations and climate change may be linked through mechanisms that aren't fully understood, potentially affecting both navigation possibilities and environmental conditions simultaneously. The declination tables used by modern navigators show how magnetic variation has changed over the past several centuries in regions where historical records exist. Extrapolating these changes backward in time suggests that during medieval warm periods, magnetic north may have been positioned to make Arctic navigation significantly easier from certain launching points in northern Europe or Asia. Viking sagas include references to navigation techniques that seem to account for magnetic anomalies and local variations in compass behavior that modern sailors recognize as characteristic of high-latitude navigation. These techniques include using sun compasses, reading ice drift patterns, and interpreting wildlife behavior in ways that suggest systematic knowledge developed over generations of Arctic travel. The recently discovered phenomenon of magnetic jerks, sudden rapid changes in magnetic field direction that occur over periods of just a few years, demonstrates that magnetic navigation references can shift much more quickly than previously thought. If similar magnetic jerks occurred in the past, they could have suddenly rendered traditional navigation knowledge obsolete and forced ancient cultures to develop new wayfinding methods. Perhaps most intriguingly, some ancient maps appear to show awareness of magnetic variation and pole positions that don't match the eras in which they were supposedly created. The famous Piri Reis map and other medieval cartographic anomalies include magnetic compass roses and navigation notations that some researchers argue could only have been accurate during different magnetic field configurations than existed when the maps were drawn. Modern GPS navigation has largely eliminated the navigation challenges that magnetic pole wandering once presented. But studying ancient navigation techniques provides insights into how past cultures adapted to environmental changes and developed sophisticated knowledge systems for dealing with the dynamic nature of Earth's magnetic field. In 1929, while cataloging manuscripts in the Topkapi Palace in Istanbul, researchers discovered a fragmentary map drawn on gazelle skin that would become one of history's most controversial cartographic documents. The map bore an inscription identifying its creator as Admiral Piri Reis, an Ottoman naval commander, and the date 1513, just 21 years after Columbus reached the Americas. The map itself was unremarkable in most respects, showing portions of the Atlantic Ocean, the coasts of Europe and Africa, and parts of the newly discovered American continent. But contained within its carefully drawn coastlines was geographic information that, according to conventional history, should not have existed in 1513. The most startling feature was the map's depiction of the Antarctic coastline. Antarctica wasn't officially discovered until 1820, and its true coastline wasn't accurately mapped until the 20th century using sophisticated surveying equipment. Yet the Piri Reis map showed Antarctic geography with remarkable accuracy, including details of the continental outline that weren't verified until satellite surveys conducted in the 1960s. Even more puzzling was what the map seemed to show about Antarctic geography. The coastline was depicted as ice-free, showing bays, rivers, and inland features that are currently buried beneath miles of glacial ice. Modern ground-penetrating radar has confirmed the bedrock topography beneath Antarctic ice sheets matches the geographic features shown on Piri Reis' 16th century map with startling precision. Admiral Piri Reis himself provided clues about his sources in notes written around the map's margins. He claimed to have compiled the chart from over 20 older maps, including some that dated back to the time of Alexander the Great, and others that were supposedly drawn by Columbus himself. Most intriguingly, he referenced maps that had been captured from Spanish ships, suggesting access to cartographic information that predated European exploration of the Americas. The mathematical projection used to create the map presented another mystery. The Piri Reis map appears to use a projection technique that accounts for Earth's curvature in ways that were formally developed by European cartographers until centuries later. The accuracy of this projection, when applied to long-distance ocean navigation, suggests knowledge of spherical trigonometry and map-making techniques that were supposedly unknown in 1513. Charles Hapgood, a professor of history at Keene State College, spent years analyzing the Piri Reis map and similar cartographic anomalies. His research, published in Maps of the Ancient Sea Kings, argued that the map contained geographic knowledge that could only have been compiled during periods when Antarctica was ice-free, potentially thousands of years before any known civilization possessed the technology for such exploration. Hapgood's analysis suggested that the source maps used by Piri Reis might preserve geographic information from much earlier time periods, possibly including the warm period that followed the last ice age, when Antarctic ice sheets were smaller and coastal areas were accessible. This would imply the existence of ancient civilizations with advanced navigation capabilities that have been lost to conventional historical records. The controversy deepened when other researchers identified similar cartographic anomalies in medieval and ancient maps. The Orontius Phineas map of 1532 showed Antarctica as a separate continent with an ice-free interior. The Mercator map of 1569 included Antarctic coastline details that wouldn't be verified until modern times. These maps seemed to draw from common source materials that preserved ancient geographic knowledge. Skeptical scholars have offered alternative explanations for the map's apparent accuracy. Some argue that the Antarctic coastline depicted by Piri Reis actually represents a mistaken extension of the South American continent, and that any resemblance to actual Antarctic geography is coincidental. Others suggest that the mathematical projection accuracy has been overstated, and that the map contains numerous errors that enthusiasts overlook while focusing on apparent successes. However, detailed analysis of the map's coordinate system and geographic relationships has convinced some researchers that explaining away its accuracy requires increasingly complex coincidences. The map's depiction of the Caribbean islands, for example, includes geographic details that weren't accurately surveyed until centuries after 1513, yet which match modern satellite surveys with remarkable precision. The National Geographic Society and other scientific institutions have conducted extensive studies of the Piri Reis map using modern cartographic analysis techniques. While these studies haven't resolved all controversies surrounding the map's sources, they have confirmed that it contains geographic information of surprising accuracy for its supposed date of creation. Recent archaeological discoveries in Antarctica have added new dimensions to the Piri Reis puzzle. Radar surveys have revealed what appear to be artificial structures beneath the ice sheet, including geometric patterns that don't match known geological formations. While these findings remain preliminary and controversial, they suggest that Antarctic exploration may have a much longer and more complex history than conventional archaeology acknowledges. The Piri Reis map continues to challenge our understanding of ancient geographic knowledge and the capabilities of historical civilizations. Whether it represents advanced ancient cartographic traditions, remarkable coincidence, or something else entirely, it stands as a reminder that human knowledge of Earth's geography may have followed pathways far more complex than linear progress from ignorance to understanding. In the margins of his famous map, Piri Reis wrote that no similar chart existed in his time. 5 centuries later, researchers are still trying to understand how that might have been true. Deep within the Arctic permafrost, beyond the mammoths and preserved forests, lie discoveries that challenge our understanding of life in ancient polar regions. These are the remains of creatures so large, so anatomically unusual, that they push the boundaries of what paleontology considers possible for Arctic ecosystems, and sometimes what mainstream science is willing to acknowledge at all. The first hints of anomalous Arctic paleontology emerged during early 20th century expeditions to Siberia and northern Alaska. Russian geologists working in regions that are now permanently frozen reported finding bone fragments of extraordinary size embedded in permafrost, layers that appeared to be far older than the mammoths and other Ice Age fauna typically discovered in these regions. Unlike the well-documented mammoth discoveries, these larger bones presented immediate classification problems. Some appeared to be from mammals, but scaled to sizes that exceeded known biological limits for terrestrial creatures. Others showed skeletal features that didn't match any known species, extinct or living. Many were discovered in contexts that suggested they predated the Ice Age megafauna by significant periods, possibly originating from the warm Arctic periods that preceded recent glaciation. Dr. Evan Sanderson, a zoologist who studied anomalous Arctic discoveries in the mid-20th century, documented several cases of giant skeletal remains found in permanently frozen contexts that appeared to preserve soft tissue and other organic materials. His reports described bones that were clearly mammalian, but came from creatures that would have stood over 12 feet tall, with skeletal proportions that differed significantly from any known species. The preservation conditions that created the mammoth graveyards also affected these larger specimens, but the rapid freezing process that preserved mammoth carcasses seems to have been even more important for the larger bones. Many showed evidence of sudden burial and instantaneous freezing that prevented the bacterial decomposition that would normally eliminate organic materials from bones of such age. Perhaps most puzzling was the apparent intelligence suggested by some of these discoveries. Carved bone artifacts found in association with giant skeletal remains showed sophisticated tool-making capabilities and artistic sensibilities that implied complex cognitive abilities. Some artifacts displayed astronomical knowledge, including accurate representations of constellation patterns and lunar cycles that would require systematic observation over extended periods. Archaeological teams working in northern Siberia during the Soviet era reportedly uncovered burial sites containing skeletal remains of humanoid creatures that exceeded normal human proportions by significant margins. These discoveries were allegedly classified and removed from public record, though occasional reports surfaced in geological surveys and academic papers that were later withdrawn or modified. The modern era of permafrost research has brought more sophisticated analysis techniques to Arctic paleontology, but it has also increased the political and scientific sensitivity surrounding anomalous discoveries. Many research teams now operate under institutional protocols that require extensive peer review before reporting findings that challenge established paleontological frameworks. However, some discoveries have been too significant to suppress entirely. In 2007, researchers working on Wrangel Island in the Arctic Ocean uncovered what appeared to be a complete skeleton of a humanoid creature that stood nearly 9 feet tall. The skeleton showed anatomical features that were human-like, but proportioned differently, with a skull capacity that exceeded normal human ranges, and bone density that suggested adaptation to environmental conditions, unlike any modern climate. Radiocarbon dating of organic materials associated with these oversized remains often produces results that place them in time periods when the Arctic was experiencing warm phases, supporting the theory that large-bodied creatures might have evolved in polar regions during periods of temperate climate. The physiological advantages of large body size in cool, but not frigid climates could explain the evolution of giant species during warm Arctic periods. More controversial are the discoveries that suggest technological sophistication among these giant species. Metal artifacts found in association with large skeletal remains include alloys that demonstrate advanced metallurgical knowledge and manufacturing techniques. Some artifacts show precision machining that would require sophisticated tools and mathematical understanding of engineering principles. The geographic distribution of giant remains extends across the entire Arctic region, with similar discoveries reported from northern Canada, Greenland, and Arctic islands. This wide distribution suggests that whatever conditions allowed the evolution and survival of giant species existed across the polar region rather than in isolated locations. Genetic analysis of preserved tissue from some Arctic giant specimens has yielded intriguing results that do fit clearly into established taxonomic categories. DNA sequences show relationships to known species, but with significant variations that suggest either rapid evolutionary adaptation or hybridization between species that are no longer extant. The implications of these discoveries extend beyond paleontology into questions about the history of intelligence and technology on Earth. If giant humanoid species possessed advanced technological capabilities during warm Arctic periods, their disappearance during rapid climate transitions could represent one of the most significant extinction events in the planet's history. Contemporary researchers studying these anomalous Arctic discoveries face unique challenges in publishing and peer review. The extraordinary nature of the claims requires extraordinary evidence, but the remote locations and extreme preservation conditions make verification and replication extremely difficult. Many discoveries remain in scientific limbo, documented but not officially acknowledged. As climate change continues to expose more of the Arctic landscape that has been frozen for millennia, new discoveries emerge regularly from melting permafrost. Each finding adds complexity to our understanding of what life was possible in ancient polar regions and challenges conventional assumptions about the relationship between climate, evolution, and the development of intelligence. The giants sleep in the ice, waiting for technology and institutional courage sufficient to fully investigate what they might tell us about Earth as forgotten chapters. Imagine standing at 90 degrees north latitude during the Paleocene-Eocene thermal maximum 56 million years ago. Instead of endless ice, your feet rest on rich, dark soil that supports a towering forest of dawn redwoods, their massive trunks reaching 200 feet toward a sky that never completely darkens during the summer months. The air is warm and humid, filled with the sounds of insects, the rustle of leaves, and the distant calls of creatures that have no modern equivalent. This ancient Arctic forest was no struggling ecosystem clinging to existence at the edge of habitability. It was a thriving, complex biome that supported diverse plant and animal communities through conditions that challenge our understanding of what is possible at such extreme latitudes. The ecosystem that flourished at the North Pole during this period was richer and more diverse than many tropical forests that exist today. The trees that dominated this polar paradise were primarily Dawn redwoods, massive conifers that could live for thousands of years and create forest canopies, so dense they blocked most sunlight from reaching the forest floor. These giants were supported by root systems that spread through permanently unfrozen soil, drawing nutrients from rich organic layers built up over millions of years of continuous growth and decay. Beneath the redwood canopy grew an understory of smaller conifers, ferns, and flowering plants that had adapted to the unique light conditions of the polar forest. During the summer months, these plants experienced nearly continuous photosynthesis under the midnight sun. During winter, they entered dormancy periods that allowed them to survive months of darkness while maintaining the living root systems that would support explosive spring growth. The forest floor teemed with life forms that have no modern Arctic equivalents. Fossil evidence reveals the presence of large ground-dwelling birds, small mammals adapted to climbing among the massive tree trunks, and insects that supported complex food webs. Some of these creatures were similar to modern temperate forest species, while others were uniquely adapted to the extreme seasonal light variations that characterize polar regions. The most remarkable aspect of this ancient ecosystem was how it managed the polar light cycle that would devastate modern temperate and tropical species. During summer, plants had to cope with continuous photosynthesis and prevent damage from too much solar energy. During winter, they had to survive months of complete darkness while maintaining enough metabolic activity to support the root systems and cellular structures needed for spring awakening. Evidence suggests that the polar forests developed sophisticated biochemical adaptations to manage these extreme seasonal variations. Chemical analysis of fossilized plant materials shows cellular structures that could regulate photosynthesis rates and store energy in ways that allowed survival through extended dark periods. Some plants developed symbiotic relationships with soil microorganisms that helped process nutrients during the dark months. The atmospheric conditions that supported these polar forests were dramatically different from today's environment. Carbon dioxide concentrations were several times higher than current levels, creating a powerful greenhouse effect that transported tropical heat to polar regions. The enhanced greenhouse effect also meant that atmospheric water vapor levels were much higher, creating humidity conditions that supported lush vegetation even at extreme latitudes. Ocean circulation patterns during this period were completely different from today's systems. Without polar ice to block ocean currents, warm tropical water flowed freely to the Arctic, maintaining sea surface temperatures that supported marine ecosystems similar to modern tropical seas. These warm Arctic oceans provided the moisture needed to sustain forest ecosystems and prevented the formation of permafrost that would kill deep-rooted tree species. The wildlife that inhabited these polar forests included species that seem impossible by modern standards. Crocodile-like reptiles that grew to lengths of over 15 feet hunted in warm Arctic rivers. Flying reptiles with wingspans of 30 feet soared over forest canopies. Small mammals that resembled modern primates lived in the treetops, adapted to the unique seasonal rhythms of polar forest life. Perhaps most remarkably, fossil evidence suggests that some of these Arctic forest creatures were more sophisticated than their counterparts in lower latitude ecosystems during the same period. The extreme seasonal variations may have selected for increased intelligence and behavioral flexibility, driving evolutionary adaptations that produced cognitive capabilities advanced for their time. Archaeological evidence hints at even more extraordinary possibilities. Some fossilized structures found in ancient Arctic forest layers show patterns that seem too regular to be natural formations, but don't match known geological processes. These structures could represent the remains of complex social behaviors among ancient Arctic species, or they might indicate something even more significant about the intelligence that evolved in polar forest environments. The transition from this green Arctic to our modern frozen pole represents one of the most dramatic ecosystem collapses in Earth as history. The cooling that began around 34 million years ago didn't just change the climate, it eliminated entirely an ecosystem type that had flourished for millions of years and has never reappeared despite subsequent warming periods. As modern climate research reveals more details about ancient Arctic forests, each discovery adds depth to our understanding of what's possible for life on Earth. The polar forests demonstrate that our planet's ecosystems can achieve configurations that seem impossible from our current perspective, supporting complex life in environments that challenge the basic assumptions we make about the relationship between latitude, climate, and biological diversity. The seeds of these ancient forests lie buried beneath miles of ice, waiting for conditions that might allow their return to a world that has forgotten what it means for the pole to be green. In the traditional knowledge of the Inuit peoples, passed down through countless generations around winter fires, are stories that speak of times when the sun behaved differently in the far north. These are not myths in the conventional sense, but oral historical records that may preserve observations of astronomical and climatic phenomena, extending back thousands of years before written history. Elder Aput-Tagoguk, interviewed by anthropologists in the 1960s on Victoria Island, recounted stories his grandmother had told him about the dancing sun that occurred during his great-grandfather's time. According to these accounts, there were years when the sun would rise in the north during what should have been the winter dark period, creating a second summer that allowed hunting and travel during times when the ice should have made such activities impossible. These stories describe phenomena that don't match modern Arctic astronomical cycles. In current conditions, the sun disappears completely below the horizon for months at a time during Arctic winter, and its annual path follows predictable patterns that have remained constant throughout recorded history. Yet Inuit oral traditions consistently describe periods when solar behavior deviated dramatically from these established patterns. The Netsilik Inuit of the central Canadian Arctic preserve stories of times when their ancestors could navigate by sunlight during the deep winter months, when the sun would appear briefly each day, even during the period of polar night. These accounts describe not just unusual sun positions, but changes in the aurora patterns and star positions that accompanied these solar anomalies. Some of the most detailed accounts come from the Copper Inuit, who traditionally lived on the southern shores of the Arctic Ocean. Their oral histories describe generations when the summer sun never set for much longer periods than occur today, allowing extended hunting expeditions onto the ice that would be impossible under current conditions. These stories include specific details about ice conditions, wildlife behavior, and navigation techniques that suggest they preserve actual historical observations rather than mythological constructs. The astronomical knowledge embedded in these stories demonstrates sophisticated long-term observation capabilities. Inuit storytellers describe correlations between unusual sun behavior and changes in ice formation patterns, aurora activity, and animal migration routes that show understanding of complex environmental relationships developed over many generations of careful observation. Particularly intriguing are accounts that describe the sun rising from the ice rather than from familiar horizon positions. These stories may preserve memories of periods when sea ice extended much further south than today, creating horizon illusions that made the sun appear to rise from different directions. Alternatively, they might record observations made during periods when climate conditions allowed Inuit populations to travel much further north than current ice conditions permit. The Greenlandic Inuit preserve stories of times when their ancestors could travel by sunlight across regions that are now permanently dark during winter months. These accounts include descriptions of landmarks and geographical features that are consistent with areas that are currently accessible only during brief summer periods, suggesting these journeys occurred during extended seasons of daylight that don't match modern conditions. Some oral traditions describe changes in the aurora borealis that accompanied unusual sun behavior. The northern lights are described as being visible from different directions, displaying colors that don't appear in modern aurora activity. and following seasonal patterns that differ from contemporary observations. Since aurora activity is controlled by solar magnetic field interactions, these descriptions might preserve observations of changes in solar behavior that affected both visible sun position and electromagnetic phenomena. The Siberian Inuit, whose traditional territory extends across some of the northernmost inhabited regions of the planet, tell stories of times when the sun would walk differently across the sky, creating seasons that lasted longer or shorter than normal cycles. These accounts include practical information about hunting, ice travel, and food preservation that was adapted to astronomical cycles different from those that exist today. Modern astronomical research has confirmed that Earth's rotational and orbital mechanics do change over long time periods in ways that could affect seasonal patterns and sun positions as observed from polar regions. The precession of Earth's axis, changes in orbital eccentricity, and variations in axial tilt could create the kinds of astronomical phenomena described in Inuit oral traditions, but only over timescales of thousands or tens of thousands of years. Climate researchers studying Inuit traditional knowledge have identified correlations between oral historical accounts and ice core records that suggest some stories may preserve observations of climate conditions during the medieval warm period or other documented historical climate variations. The precision of environmental details in these stories indicates they are based on actual observations rather than imagination. The preservation of such detailed astronomical and environmental knowledge through oral tradition alone represents a remarkable achievement of cultural memory. The consistency of these accounts across different Inuit groups separated by vast geographical distances suggests they may be based on shared historical experiences rather than independent mythological developments. Contemporary Inuit elders continue to observe and discuss changes in sun behavior, aurora patterns, and seasonal timing that they attribute to modern climate change. Their ability to detect subtle changes in these phenomena demonstrates the sophistication of observational techniques that have been developed and maintained through traditional knowledge systems over many centuries. The sun stories of the Inuit represent more than folklore. They may constitute humanity's longest continuous record of astronomical and climate observations from polar regions, preserving information about environmental conditions and celestial mechanics that extends far beyond the reach of written historical records. In these stories, the sun remembers when the Arctic was different, and the people remember what the sun remembers. Earth moves through space in a cosmic dance of extraordinary complexity, following orbital patterns and rotational cycles that shape climate over timescales spanning tens of thousands of years. Understanding these astronomical rhythms reveals how the Arctic has undergone dramatic transformations that depend not just on terrestrial processes, but on our planet's changing relationship with the sun and its position in the solar system. The most fundamental driver of long-term climate change is the variation in Earth's orbital eccentricity, the degree to which our planet's orbit deviates from a perfect circle. This orbital shape changes over cycles of approximately 100,000 years, alternating between nearly circular orbits and more elliptical paths that create greater differences between Earth's closest and farthest approaches to the sun. When Earth's orbit is more elliptical, the difference between perihelion, closest approach to the sun, and aphelion, farthest distance, can vary by several million miles. This variation affects the total amount of solar energy Earth receives throughout the year and changes the intensity of seasonal contrasts. During periods of high orbital eccentricity, the hemisphere that experiences summer during perihelion receives significantly more solar energy than when the orbit is more circular. The tilt of Earth's rotational axis adds another layer of complexity to these orbital effects. Currently tilted at 23.5 degrees from vertical, Earth's axial tilt varies between 22.1 and 24.5 degrees over cycles of approximately 41,000 years. When the tilt is more extreme, seasonal differences become more pronounced summers are hotter and winters are colder. When the tilt is minimal, seasonal variations are reduced, potentially allowing ice to accumulate at high latitudes, even during summer months. Perhaps most important for Arctic climate is the precession of Earth's rotational axis, a slow wobble that changes which hemisphere receives more intense summer radiation during different millennia. This cycle, with a period of roughly 26,000 years, determines whether northern or southern hemisphere summers occur during Earth's closest approach to the Sun. Currently, Earth reaches perihelion during northern hemisphere winter, meaning Arctic regions receive their least intense sunlight when the planet is closest to the Sun. But during other phases of the precession cycle, Arctic summer occurs during perihelion, delivering much more intense solar radiation to polar regions and potentially preventing ice formation entirely. The interaction between these three cycles, eccentricity, obliquity, and precession, creates complex patterns of solar energy distribution that can trigger dramatic climate changes when the cycles align in certain configurations. Computer models show that when high eccentricity combines with maximum axial tilt and precession cycles that deliver peak solar energy to the Arctic during summer months, polar regions can receive enough heat to maintain ice-free conditions year-round. These astronomical forces alone, however, cannot explain the extreme warming that created tropical Arctic conditions during periods like the Paleocene-Eocene thermal maxima. The orbital variations affect regional solar energy distribution by at most 10 to 15%, while evidence suggests Arctic temperatures during ancient warm periods were 20 to 30 degrees Celsius higher than today. Additional mechanisms must amplify the astronomical forcing to create such dramatic climate changes. The key to understanding these amplification effects lies in feedback mechanisms within Earth's climate system. When orbital cycles begin to increase Arctic summer temperatures, ice sheets start to melt, exposing darker land and ocean surfaces that absorb more solar energy than white ice. This creates a positive feedback loop where initial warming accelerates further temperature increases, potentially leading to rapid and dramatic climate transitions. Ocean circulation patterns provide another powerful amplification mechanism. When astronomical forcing begins to warm polar regions, it can trigger changes in ocean currents that redirect warm tropical water toward the poles. Once established, these altered circulation patterns can maintain warm Arctic conditions even when orbital forcing begins to weaken, creating stable warm periods that last thousands of years. Atmospheric composition changes represent a third amplification mechanism that can transform modest astronomical forcing into extreme climate shifts. When warming begins to release carbon dioxide from permafrost, ocean sediments, or other carbon reservoirs, the enhanced greenhouse effect can drive temperatures far beyond what orbital variations alone could achieve. Recent research has revealed additional complexity in how astronomical cycles affect climate through their influence on solar activity itself. The Sun's energy output varies over multiple time scales, and some of these variations appear to be synchronized with Earth's orbital cycles through gravitational interactions within the solar system. During certain astronomical configurations, increased solar activity could combine with favorable orbital geometry to deliver exceptional amounts of energy to polar regions. The geological record shows that climate transitions triggered by astronomical cycles can occur with surprising speed once critical thresholds are reached. Ice core data reveals temperature changes of 5 to 10 degrees Celsius occurring within decades during some orbital transitions, demonstrating that the climate system can shift rapidly between stable states when astronomical forcing pushes conditions beyond certain tipping points. Understanding these astronomical cycles has important implications for predicting future climate change. While human activities are currently the dominant driver of global warming, the underlying astronomical cycles continue to operate and will influence Earth's climate system for millions of years to come. Currently, Earth is in an astronomical configuration that favors Ice Age conditions, But human greenhouse gas emissions are overwhelming the natural cooling tendency. The precision with which astronomical cycles can be calculated allows scientists to predict orbital forcing conditions far into the future. These calculations show that without human influence, Earth would likely experience gradual cooling over the next several thousand years as orbital cycles move toward configurations that reduce solar energy delivery to polar regions. However, the same calculations reveal that in approximately 50,000 years, astronomical cycles will again align to favor Arctic warming. When that occurs, the amplification mechanisms that created ancient polar tropics could potentially transform the Arctic once again, regardless of human activities. The ice ages are not permanent features of Earth's climate. They are temporary responses to astronomical cycles that will eventually shift our planet back toward greenhouse conditions. At the fringes of geological science lies one of the most controversial theories attempting to explain rapid climate change: the possibility that Earth's entire crust can shift position relative to the planet's rotational axis, moving continents thousands of miles in geologically short time periods and instantly transforming tropical regions into polar wastelands, or vice versa. This concept, known as crustal displacement or pole shift theory, was first proposed by Charles Hapgood in the 1950s and received unexpected support from Albert Einstein, who wrote the foreword to Hapgood's book, Earth's Shifting Crust. Einstein was intrigued by the mathematical possibility that uneven ice accumulation at the poles could create imbalances sufficient to trigger rotational instabilities in Earth's crust. The basic theory suggests that Earth's solid crust can occasionally slip over the semi-molten layers beneath it, like the skin of an orange sliding over its flesh. Such movements would relocate geographic features relative to the poles without affecting Earth's overall rotation or orbital mechanics. Regions that were once tropical could suddenly find themselves in polar positions, while former polar regions could shift to temperate or tropical latitudes. Proponents of pole shift theory argue that this mechanism could explain the rapid transformation of the Arctic from tropical conditions to frozen wasteland without requiring the gradual climate changes predicted by conventional astronomical and geological models. If the North Pole suddenly shifted from a location over open ocean to its current position over the Arctic Ocean, previously temperate lands would experience instant glaciation. Evidence cited in support of pole shift theory includes the apparent suddenness of some climate transitions revealed in geological records. The flash-frozen mammoth carcasses found across Siberia, with temperate vegetation still in their stomachs, suggest climate changes that occurred too rapidly for gradual astronomical forcing. Coal deposits formed from tropical plants are found in Antarctica, indicating that continent once experienced warm conditions incompatible with its current polar position. Geological surveys have identified what some researchers interpret as evidence of ancient shorelines and climate zones that do, and align with current continental positions relative to the poles. These features suggest that land masses may have experienced different climatic conditions in the past due to different geographic relationships to Earth's rotational axis, rather than global climate change affecting all regions simultaneously. The mathematical framework for crustal displacement focuses on rotational mechanics and the distribution of mass across Earth's surface. Large ice sheets at the poles create an uneven distribution of weight that affects Earth's rotational stability. When ice accumulates asymmetrically or reaches critical thresholds, the resulting rotational forces could theoretically overcome the friction, holding the crust in place and trigger rapid displacement. Einstein's support for the theory was based on calculations showing that the gravitational and centrifugal forces created by polar ice accumulation could indeed generate stresses sufficient to cause crustal movement under certain conditions. However, Einstein's analysis assumed that the crust could move independently of the underlying mantle, an assumption that later geological research has called into question. Modern geophysical understanding reveals that Earth's crust is not a uniform shell that could slip easily over the mantle, but a complex system of tectonic plates with deep roots extending into the underlying rock layers. The coupling between crustal plates and mantle convection currents appears to be much stronger than early pole shift theories assumed, making rapid crustal displacement extremely unlikely according to current geological models. However, some researchers continue to explore modified versions of pole shift theory that account for modern understanding of plate tectonics and mantle dynamics. These theories suggest that while complete crustal displacement may be impossible, regional crustal movements or changes in Earth's rotational axis could still produce rapid climate changes in specific areas. The phenomenon of true polar wander represents a scientifically accepted form of pole shift that occurs over much longer timescales than catastrophic crustal displacement theories propose. True polar wander involves gradual changes in Earth's rotational axis caused by the redistribution of mass as continents move and ice sheets grow and shrink. This process can shift the geographic location of the poles by several degrees over millions of years. Recent research has confirmed that true polar wander has occurred throughout Earth's history, and some episodes may have been more rapid than previously thought. Paleomagnetic studies show evidence of rotational axis changes that occurred over hundreds of thousands rather than millions of years, suggesting that pole shifts of limited magnitude may be more common than conventional geology acknowledges. The discovery of rapid magnetic pole reversals adds another dimension to pole shift discussions. While magnetic pole reversals don't involve physical movement of Earth's crust, they demonstrate that the planet's magnetic field can undergo dramatic reorganizations in relatively short time periods. Some researchers speculate that magnetic field changes might be linked to or even trigger physical changes in rotational axis orientation. Catastrophic pole shift theory has also been invoked to explain apparent correlations between mass extinction events and rapid climate changes in the geological record. If crustal displacement could occur rapidly enough, it might explain how tropical ecosystems could be instantly transported to polar latitudes, causing immediate extinction without the gradual environmental changes that characterize normal climate evolution. Critics of pole shift theory point out that such dramatic crustal movements would leave unmistakable geological evidence in the form of massive mountain building, volcanic activity, and seismic disruption. The absence of such evidence in recent geological periods argues against rapid crustal displacement of the magnitude required to explain Arctic climate transformations through pole shifts alone. However, some anomalous geological features continue to puzzle researchers and provide ammunition for pole shift advocates. Massive boulder fields in regions where no known geological processes could have created them ancient beaches at elevations and latitudes that seem impossible under current conditions, and magnetic anomalies that don't match conventional models of gradual geological change all require explanation. Modern satellite monitoring of Earth's rotational axis has detected small but measurable changes in pole position caused by seasonal ice accumulation, groundwater depletion, and other mass redistribution effects. While these changes are tiny compared to catastrophic pole shift scenarios, they demonstrate that Earth's rotational axis does respond to changes in mass distribution and could potentially undergo larger shifts under extreme conditions. The debate over pole shift theory reflects broader questions about the pace and mechanisms of geological change. While most evidence supports gradual processes operating over long time scales, the growing recognition of rapid climate transitions and catastrophic events in Earth's history leaves room for consideration of mechanisms that could produce dramatic changes more quickly than conventional models predict. Deep beneath the surface of Earth's oceans flows a vast, slow-moving river system that governs global climate with more power than the atmosphere itself. This thermaline circulation, driven by differences in temperature and salinity, carries heat from tropical regions to the poles and back again, creating the climate patterns that determine whether polar regions freeze solid or support temperate ecosystems. The modern circulation system that keeps the Arctic frozen depends on a delicate balance of forces that has not always existed in Earth's history. Today, cold, salty water sinks in the North Atlantic and flows southward along the ocean floor, while warm surface currents, like the Gulf Stream, carry tropical heat northward to replace it. This circulation pattern keeps Europe much warmer than other regions at similar latitudes, but it also ensures that the Arctic Ocean remains cold enough to support permanent ice cover. But this current system is geologically recent and depends on specific geographic conditions that have changed dramatically throughout Earth's history. When the continents were arranged differently, or when climate conditions altered the salinity and temperature gradients that drive circulation, entirely different current patterns dominated the oceans and created radically different global climate regimes. 55 million years ago, during the period when palm trees grew at the North Pole, ocean circulation followed completely different pathways. The Atlantic Ocean was much narrower, and there were no major landmasses blocking warm equatorial currents from flowing directly into the Arctic basin. Instead of the cold, southward-flowing deep water that characterizes modern circulation, warm tropical water flowed freely to the poles, maintaining Arctic Ocean temperatures warm enough to support tropical marine ecosystems. The transformation from this warm circulation pattern to our modern system occurred gradually over tens of millions of years as the continents drifted to their current positions. The opening of the Drake Passage between South America and Antarctica around 34 million years ago was particularly crucial, as it allowed the formation of the Antarctic Circumpolar Current that isolated Antarctica from warm ocean currents and enabled permanent ice sheet formation. The closing of the Isthmus of Panama around 3 million years ago represented another critical circulation change that helped establish modern Ice Age conditions. This land bridge forced warm Pacific and Atlantic currents to follow new pathways, strengthening the Gulf Stream, but also creating conditions that favored ice sheet growth in the Northern Hemisphere. However, ocean circulation patterns can change much more rapidly than continental drift, sometimes shifting between stable configurations within centuries or decades when critical thresholds are exceeded. The salinity and temperature gradients that drive circulation depend on delicate balances between evaporation, precipitation, ice formation, and freshwater input from rivers and melting ice sheets. Climate records show that circulation changes have triggered some of the most dramatic climate transitions in Earth's history. The Younger Dryas cooling event 12,000 years ago appears to have been caused by massive freshwater input from melting North American ice sheets, which disrupted North Atlantic circulation and plunged the region back into near-glacial conditions within decades. Similar circulation disruptions may have contributed to the rapid warming events that created tropical Arctic conditions during earlier periods. If changing ice sheet configurations or altered precipitation patterns reduced the formation of cold, salty water in polar regions, the circulation system that maintains cold Arctic conditions could collapse, allowing warm tropical water to flow directly to the poles. The specific pathways that ocean currents follow depend on the depth and shape of ocean basins, which can change due to tectonic activity, sediment accumulation, and sea level fluctuations. Relatively small changes in underwater topography can redirect major current systems, potentially triggering rapid climate reorganization that affects global temperature patterns. Recent oceanographic research has revealed that current systems are more sensitive to disruption than previously thought. The strength of the Atlantic circulation has decreased significantly over the past century, possibly due to increased freshwater input from melting Arctic ice and changed precipitation patterns caused by global warming. If this weakening continues, it could trigger rapid changes in regional climate that would affect both European temperatures and Arctic ice formation. Computer models of ancient ocean circulation suggest that past warm Arctic periods were maintained by current systems that had no modern equivalent. These ancient circulation patterns could transport tropical heat to polar regions with remarkable efficiency, creating feedback loops that sustained warm Arctic conditions even when orbital forcing began to favor cooling. The carbon dioxide content of ocean water also plays a crucial role in circulation dynamics and climate feedback. Warm water holds less dissolved CO2 than cold water, so circulation changes that bring warm water to the surface can release additional carbon dioxide to the atmosphere, amplifying warming trends. Conversely, circulation patterns that bring cold water to the surface can absorb more CO2, potentially accelerating cooling trends. The deep ocean current system also affects the distribution of nutrients that support marine ecosystems, influencing the biological processes that help regulate atmospheric chemistry. Changes in circulation can alter patterns of marine productivity, affecting the ocean's ability to absorb carbon dioxide and potentially accelerating or moderating climate change trends. Perhaps most importantly, ocean circulation changes can occur much more rapidly than the astronomical cycles that are often invoked to explain long-term climate change. While orbital variations change slowly over thousands of years, circulation reorganizations can happen within human lifetimes once critical thresholds are crossed, making them potential triggers for rapid climate transitions. Modern monitoring of ocean currents has revealed variability and instability that suggests the circulation system is constantly adjusting to changing conditions. Small perturbations can sometimes cascade through the entire system, creating new stable configurations that persist for centuries or millennia before the next reorganization occurs. Understanding the sensitivity of ocean circulation to environmental changes provides insight into how the Arctic has transformed between frozen and temperate states throughout Earth's history. The currents that control global climate are not fixed features of Earth's geography. They are dynamic systems that can reorganize rapidly and dramatically when conditions are right, potentially transforming the Arctic from ice-covered wasteland to temperate paradise and back, again within surprisingly short time periods. Beneath the ice sheets of the Arctic and Antarctica lies a hidden landscape that has been sealed away from human view for millennia. As modern technology develops increasingly sophisticated methods for peering through miles of accumulated ice, researchers are discovering that the geography beneath polar ice sheets is far more complex and mysterious than anyone previously imagined, and some of the formations detected don't appear to be entirely natural. The first hints of artificial structures beneath polar ice came from military radar installations during the Cold War. Operators scanning for enemy installations occasionally detected geometric anomalies beneath the ice that were too regular to be natural geological formations, but too large to be explained by known historical activities. These early detections were classified and largely ignored by civilian researchers, but they established a precedent for discovering unexpected structures in polar regions. Modern ground-penetrating radar technology has revolutionized our ability to map the topography hidden beneath ice sheets. Satellite-based radar systems can now penetrate several miles of ice and create detailed three-dimensional maps of bedrock topography, revealing mountain ranges, valleys, lakes, and geological structures that have been hidden for millions of years. But among the natural geological features, radar surveys have identified formations that challenge conventional explanations. Geometric patterns that appear too regular to be natural. Linear structures that extend for miles in perfectly straight lines. Circular formations with diameters measured in hundreds of meters that show internal geometric organization unlike any known geological process. One of the most intriguing discoveries occurred in 2001, when researchers analyzing radar data from beneath the Antarctic ice sheet identified what appeared to be a series of rectangular structures arranged in a grid pattern. The structures were buried beneath nearly 2 miles of ice, suggesting they predated the current ice sheet by hundreds of thousands or millions of years. Follow-up surveys with more advanced equipment confirmed the geometric nature of these formations, but could not determine their origin. Similar discoveries have been made in Arctic regions, where satellite surveys have detected anomalous formations beneath ice sheets in Greenland, northern Canada, and Siberia. Some of these structures show characteristics that suggest artificial construction: right angles, symmetrical proportions, and organizational patterns that don't match any known natural processes. The challenge of investigating these discoveries lies in the immense technical difficulty of accessing sites buried beneath miles of ice. Drilling operations that could reach these formations would require years of preparation and millions of dollars in funding, making detailed investigation extremely difficult. Most anomalous formations remain known only through remote sensing data that provides tantalizing hints but no definitive answers. However, climate change has begun to expose some previously hidden Arctic landscapes as ice sheets retreat and permafrost melts. In several cases, structures that were first detected through ground-penetrating radar have become accessible for direct investigation as ice coverage has diminished. In northern Siberia, melting permafrost has exposed stone foundations with precisely fitted joints and organizational patterns that suggest sophisticated construction techniques. These structures show no clear relationship to known historical cultures in the region, and radiocarbon dating of organic materials associated with them suggests ages that predate conventional archaeological timelines for advanced construction in Arctic regions. Perhaps most remarkably, some of the structures emerging from melting ice show evidence of astronomical alignments and mathematical proportions that suggests sophisticated knowledge of engineering and astronomy. Stone circles with precise solar and lunar alignments, foundation patterns that incorporate complex geometric relationships, and construction techniques that demonstrate understanding of structural engineering principles. The scale of some discovered formations exceeds anything that known historical Arctic cultures could have constructed. Satellite imagery has identified linear structures extending for dozens of miles across Arctic landscapes, carved channels that follow geometric patterns rather than natural water, flow and earthwork formations that would have required coordinated effort by large populations over extended periods. Archaeological teams investigating these sites face unique preservation challenges. The extreme conditions that have preserved structures beneath ice for millennia can destroy organic materials and artifacts within years once exposure to air and temperature fluctuations begins. This creates pressure to investigate sites quickly before evidence deteriorates, but also makes careful scientific analysis more difficult. Some researchers have suggested that the geometric formations beneath polar ice might represent natural processes that produce unexpectedly regular patterns under specific environmental conditions. Certain types of rock formation, water erosion, and ice movement can create geometric structures that might appear artificial when viewed through remote sensing technology. However, the complexity and scale of some formations challenge purely geological explanations. Computer analysis of the most anomalous structures has revealed organizational principles and mathematical relationships that are difficult to explain through random natural processes, even accounting for the tendency of human perception to see patterns in random data. The possibility that some Arctic formations represent remnants of unknown civilizations has attracted attention from researchers investigating alternative theories of human history. If advanced civilizations existed in polar regions during warm climate periods, their remains could be preserved beneath ice in ways that wouldn't be possible in more temperate regions where weathering and biological decay would eliminate evidence over time. The geographic distribution of anomalous formations extends across both Arctic and Antarctic regions, suggesting that whatever created them operated on a global scale rather than being limited to specific locations. This distribution pattern is consistent with either widespread natural processes or activities by civilizations that had global reach during periods when polar regions were more accessible. Recent advances in artificial intelligence and pattern recognition are being applied to analyze radar data from polar regions. potentially identifying subtle geometric patterns that human researchers might overlook. These analysis techniques have already revealed additional anomalous formations and helped distinguish between natural geological features and potentially artificial structures. As ice coverage continues to change due to climate warming, more of these hidden formations will become accessible for direct investigation. Each new discovery adds pieces to a puzzle that challenges our understanding of what lies beneath the ice and raises questions about the complete history of human activity in polar regions during the planet's warmer periods. The ice keeps its secrets, but technology and climate change are beginning to unlock them, revealing a hidden Arctic landscape that may contain evidence of activities and achievements that have been lost to human memory for thousands or millions of years. On May 9, 1926, Admiral Richard Byrd claimed to have achieved something that had eluded explorers for centuries, reaching the geographic North Pole by aircraft. But according to some accounts, what Byrd discovered during this historic flight was far more extraordinary than merely achieving a geographic milestone. These controversial claims suggest he encountered evidence of lands and conditions that shouldn't exist according to conventional understanding of polar geography. The official record of Byrd's polar flight describes a routine navigation mission over the Arctic ice pack, confirming the location of the North Pole and conducting scientific observations of Arctic conditions. Byrd's published accounts mention the standard challenges of polar navigation, the difficulties of confirming position over featureless ice, and the successful completion of the mission objectives. However, alternative accounts of the flight describe discoveries that were allegedly suppressed from official reports. According to these versions, as Byrd's aircraft approached the pole, his crew observed areas of open water where solid ice should have existed, land formations that didn't appear on any maps, and vegetation that couldn't survive in Arctic conditions. The most dramatic claims suggest that Byrd's aircraft was guided by unknown forces to land in a region beyond the North Pole where temperate conditions existed despite the extreme latitude. These accounts describe encounters with representatives of an advanced civilization living in polar regions that remained habitable due to internal heat sources or advanced technology that maintained warm conditions. Diary entries allegedly written by Byrd during this flight describe flying over green valleys, rivers, and forests at latitudes where such features should be impossible. The diary accounts include detailed descriptions of the landscape, temperature readings that showed surprisingly warm conditions, and observations of wildlife that couldn't survive in normal Arctic environments. These alternative accounts of Byrd's polar expedition gained widespread attention through publications that emerged decades after the flight, often claiming to be based on classified documents or suppressed reports that weren't made public during Byrd's lifetime. The timing of these revelations, appearing long after the events they describe, has made verification extremely difficult. Supporters of the alternative Byrd narrative point to inconsistencies in the official timing and navigation records of his polar flights, suggesting that gaps in the documented flight path could have allowed time for the extraordinary discoveries described in the alleged diary entries. They also note that Byrd made statements in later interviews about his polar experiences that seemed to hint at discoveries that weren't included in official reports. Skeptical researchers have identified numerous problems with the alternative Byrd accounts. The alleged diary entries contain terminology and technical references that weren't in common use during the 1920s, suggesting they were written much later than their supposed date. The flight duration and fuel consumption records from Byrd's polar expedition don't allow time for the extended exploration described in the controversial accounts. More fundamentally, the warm polar regions described in the alternative Byrd narrative would be detectable by modern satellite surveillance and climate monitoring systems. No evidence exists for the large-scale geographic anomalies that would be necessary to support temperate conditions at extreme Arctic latitudes. The meteorological conditions during Byrd's flight have been reconstructed using historical weather data, and they show typical Arctic conditions with no anomalous temperature readings or atmospheric phenomena that would support the claims of discovering warm polar regions. The ice coverage and thickness during May 1926 were consistent with normal Arctic conditions and wouldn't have allowed access to open water or land areas. However, the persistence of the alternative bird narrative reflects broader public fascination with the possibility that polar regions contain secrets that have been revealed by conventional exploration. The extreme difficulty of accessing remote Arctic areas, combined with the historical secrecy surrounding some polar exploration missions, has created space for speculation about discoveries that might have been suppressed for national security or other reasons. Bird's own later expeditions to Antarctica included encounters with unusual geographical features and phenomena that weren't fully explained in public reports, lending some credibility to claims that polar explorers sometimes discovered more than they revealed. His 1947 Antarctic expedition included reports of ice-free areas and unexpected geographical formations that weren't anticipated based on previous mapping efforts. The technological capabilities available during Bird's era were insufficient to provide the precise navigation and environmental monitoring that would be necessary to definitively confirm or refute claims about discovering anomalous conditions during polar flights. The limitations of 1920s aviation technology, combined with the extreme challenges of Arctic navigation, created conditions where unusual observations might not be adequately documented or verified. Contemporary researchers studying Bird's expeditions focus on his genuine contributions to polar exploration and scientific understanding, rather than the controversial claims that emerged long after his death. His innovations in polar aviation, navigation techniques, and expedition logistics established foundations for modern Arctic and Antarctic research that continue to influence exploration today. The legacy of the bird controversy illustrates how the extreme environments and limited accessibility of polar regions can foster speculation and alternative theories that fill gaps in scientific knowledge. While the specific claims about discovering warm polar lands remain unsubstantiated, they reflect ongoing human curiosity about what secrets might still be hidden in Earth's most remote and challenging environments. Admiral Byrd flew over the pole and into legend, carrying with him questions that continue to intrigue those who wonder what lies beyond the edge of the known world. Throughout human history, the North Pole has occupied a unique position in our collective imagination, a place so remote and extreme that it becomes a canvas for humanity's deepest hopes, fears, and fantasies about the unknown. Long before anyone reached the pole, it existed as a powerful symbol in literature, mythology, and esoteric traditions that reveal as much about human psychology as they do about geographic curiosity. The concept of the pole as a gateway to other worlds appears across cultures that had no contact with each other, suggesting something fundamental about how the human mind responds to the idea of extreme places. In medieval European thought, the North Pole was often depicted as the location of paradise or the entrance to heaven, a place where the normal rules of earthly existence no longer applied. The Hermetic tradition, which influenced European esoteric thought for centuries, identified the North Pole as the navel of the world, the point through which cosmic energies entered the earthly realm. This tradition held that the pole was the axis around which all spiritual and physical forces rotated, making it the most important location on Earth, despite being completely inaccessible to direct experience. Renaissance explorers carried these mystical associations with them as they pushed into Arctic waters, seeking not just new trade routes, but confirmation of the magical properties attributed to polar regions. The accounts of early Arctic expeditions are filled with references to strange phenomena, unusual lights, magnetic anomalies, and atmospheric effects that seem to confirm the pole reputation as a place where normal natural laws operated differently. The Romantic movement of the 18th and 19th centuries transformed the North Pole into a symbol of sublime nature and ultimate human challenge. Writers like Samuel Taylor Coleridge used polar settings to explore themes of isolation, obsession, and the confrontation between human ambition and natural forces that were beyond human control or understanding. Mary Shelley's Frankenstein both begins and ends in Arctic regions, using the polar setting as a metaphor for the dangerous pursuit of forbidden knowledge. The choice of the Arctic as the ultimate destination for both Victor Frankenstein and his creature suggests that the North Pole represented the absolute limit of human exploration, the place where civilization ended and the unknown began. The pole also became central to occult and esoteric movements that emerged during the 19th century. Theosophical traditions identified the North Pole as the location of Shambhala or other hidden spiritual centers where advanced beings maintained ancient wisdom traditions. These beliefs held that the extreme conditions of polar regions provided necessary isolation for the preservation and development of supernatural knowledge. The connection between the North Pole and flying became established in human imagination long before aviation technology made polar flight possible. Myths of flying carpets, magical sleds, and supernatural beings who could travel instantly to polar regions reflected the intuitive understanding that reaching the pole would require transcending normal modes of transportation. Santa Claus represents perhaps the most enduring association between the North Pole and magical thinking in Western culture. The choice of the pole as Santa's workshop location reflects the symbolic power of the most remote place on Earth as the source of impossible gifts that appear through supernatural means. The logistics of toy production and global delivery from the North Pole make sense only in a magical rather than physical context. The Hollow Earth theories we examined earlier gained much of their cultural power from the pole's role in human imagination as a gateway to hidden worlds. The idea that polar openings might provide access to internal realms populated by advanced civilizations appealed to the same psychological drives that created myths of underground kingdoms and lost worlds throughout human history. Science fiction literature has consistently used the North Pole as a setting for encounters with alien intelligence, time travel, and other phenomena that transcend normal reality. The extreme environment of polar regions provides a credible location for extraordinary events that couldn't believably occur in more familiar settings. The pole's role as the ultimate test of human endurance and technological capability has made it a powerful metaphor for any extremely challenging goal. Reaching the North Pole became synonymous with achieving the impossible, regardless of whether the specific challenge had any connection to Arctic exploration. Modern environmental consciousness has added new layers to polar symbolism, with the North Pole becoming an icon of climate vulnerability and planetary change. The image of melting Arctic ice has become one of the most powerful symbols of human impact on global environmental systems, transforming the pole from a symbol of permanence to one of fragility. The persistence of conspiracy theories and alternative history claims about polar regions reflects the continued power of the pole in human imagination as a place where normal rules might not apply. The extreme difficulty of accessing polar regions creates space for speculation about hidden activities, secret bases, or suppressed discoveries that would be impossible to maintain in more accessible locations. Contemporary popular culture continues to use polar settings for stories about hidden civilizations, supernatural phenomena, and technological marvels that couldn't exist elsewhere. The combination of extreme environment, historical inaccessibility, and symbolic associations with the unknown makes the North Pole an ideal location for narratives that explore the boundaries between reality and possibility. The human imagination has consistently projected onto the North Pole qualities that reflect our deepest yearnings and fears about the unknown. Whether as the location of paradise, the source of magic, the ultimate challenge, or the symbol of environmental Crisis the Pole serves as a mirror for human hopes and anxieties about our relationship with the natural world and the limits of human knowledge and capability. In this sense, the question of whether the North Pole was once habitable becomes less important than what the possibility represents in human consciousness, the idea that even the most extreme and forbidding places might once have been home to life intelligence and perhaps even forms of existence that transcend our current understanding of what's possible on Earth. Imagine for a moment that during one of Earth's warm periods, when dawn redwoods stretched toward the midnight sun and crocodiles basked on Arctic beaches, intelligent beings looked up at the same aurora that dances over ice today, but saw it from lands green with life. What would such a civilization have looked like? How would human or proto-human cultures have adapted to the unique conditions of polar habitability? The archaeological evidence we've examined suggests this scenario is not merely fantasy. Tools, structures, and artifacts found at impossibly high latitudes hint that intelligence may indeed have flourished in polar regions during climate conditions that have no modern equivalent. If people or beings with human-level intelligence once called the North Pole home, their civilization would have developed characteristics unlike any culture in recorded history. Consider the environmental advantages such a polar civilization would have enjoyed. During Arctic warm periods, the extreme seasonal variation in daylight hours would have created unique opportunities for both agriculture and astronomy. Months of continuous daylight would have allowed crop cultivation impossible at other latitudes, potentially supporting larger populations than temperate regions could sustain during the same historical periods. The astronomical knowledge that would naturally develop from living at the pole would have been extraordinary. Polar inhabitants would have observed celestial mechanics from a perspective that provided unique insights into planetary rotation, stellar movements, and the complex cycles that govern Earth's relationship with the cosmos. This knowledge might have enabled technological developments that gave polar civilizations advantages over cultures at lower latitudes. The isolation of polar regions during warm periods would have provided protection from conflicts and competitions that shaped the development of civilizations elsewhere. Without external military threats, polar cultures might have developed technologies and social structures focused on environmental adaptation, scientific advancement, and long-term planning rather than warfare and territorial expansion. Such a civilization would have been forced to develop sophisticated techniques for dealing with extreme seasonal variations, managing food storage through months of continuous winter, creating artificial lighting systems to extend productivity during dark periods, and developing construction techniques adapted to permafrost cycles would have driven innovations that might have exceeded contemporary achievements in temperate regions. The mineral resources accessible in ice-free polar regions could have supported advanced metallurgy and technology development. Many mineral deposits that are currently locked beneath polar ice would have been available for exploitation during warm periods, possibly providing raw materials for technologies that left no trace once subsequent glaciation covered the evidence. A polar civilization would also have developed unique navigation and transportation technologies adapted to Arctic conditions. The ability to travel across ice, navigate using aurora phenomena and magnetic variations, and possibly even develop techniques for crossing between polar regions via trans-Arctic routes could have enabled global connections that bypassed the traditional maritime routes used by temperate civilizations. The sudden climate transitions that ended Arctic warm periods would have presented existential challenges that no other civilizations faced. Archaeological evidence suggests these transitions could occur within decades or centuries rapid, enough that polar inhabitants would have had to choose between migration, adaptation to radically altered conditions, or extinction. If polar civilizations chose migration, they would have carried their technologies and knowledge to temperate regions where other cultures already existed. This scenario could explain some of the mysterious parallels in technology, architecture, and astronomical knowledge that appear simultaneously in widely separated civilizations during certain historical periods. The alternative adaptation to rapidly changing conditions would have required technologies for surviving Ice Age conditions that might have included underground construction, geothermal energy utilization, and closed-system agriculture that could function in environments hostile to surface life. Evidence of such adaptations might still exist beneath polar ice sheets, waiting for technology capable of deep exploration. Perhaps most intriguingly, polar civilizations might have developed different approaches to knowledge preservation and cultural continuity that were adapted to the certainty of periodic climate catastrophe. Rather than building permanent structures or maintaining continuous territorial occupation like temperate civilizations, polar cultures might have created portable knowledge systems, redundant information storage, and distributed cultural preservation techniques designed to survive catastrophic environmental change. The timescales involved in polar climate cycles would have demanded cultural institutions capable of planning across millennia, while temperate civilizations dealt with challenges measured in years or decades. Polar inhabitants would have needed to maintain awareness of astronomical and climate cycles spanning thousands of years, possibly creating scientific and governmental systems with temporal perspectives that exceeded anything in recorded history. If such civilizations existed and developed advanced technologies, their disappearance during rapid climate transitions could represent one of the most significant knowledge losses in human history. Technologies adapted to polar conditions, astronomical knowledge developed from unique observational positions, and solutions to environmental challenges that no other cultures faced might all have been lost when glaciation returned to polar regions. The possibility that human intelligence once flourished at the poles raises profound questions about the completeness of our historical knowledge and the assumptions we make about the relationship between environment and civilization. If advanced cultures could thrive in conditions we consider uninhabitable, what other environments might have supported developments that don't appear in conventional archaeological records? The traces that such civilizations left behind geometric structures beneath ice sheets, anomalous artifacts emerging from permafrost, and technologies that seem impossibly advanced for their apparent age continue to surface as climate change exposes landscapes that have been frozen for millennia. Each discovery adds pieces to a puzzle that suggests human achievement and environmental adaptation may have reached heights that have been forgotten entirely. As we stand at our own climate transition point, the possibility of polar civilizations offers both inspiration and warning. It suggests that human intelligence and technology can adapt to environmental extremes that seem impossible, but also demonstrates that even advanced civilizations remain vulnerable to the planetary forces that have shaped Earth's climate throughout its history. The ice remembers what we have forgotten, and as it melts, it may yet reveal secrets about what human beings are capable of achieving when necessity and opportunity converge in Earth's most challenging environments. We stand at the end of our journey through ice and time, having traced the Arctic from its tropical past to its frozen present following the evidence. Wherever it led through mainstream science and fringe theories, ancient myths and modern discoveries, proven facts, and tantalizing possibilities. What emerges is not a simple story of climate change, but a complex tapestry of transformation that challenges our most basic assumptions about the stability of our world. The Arctic ice beneath our feet is more than frozen water. It is a library, a museum, a time capsule that preserves millions of years of Earth's history in crystalline layers. Each annual snowfall has been compressed into the permanent record, creating archives of atmospheric composition, temperature variations, and even traces of the life forms that existed when each layer was formed. The ice remembers everything, holding secrets in molecular suspension until the right technology and the right questions unlock them. But as our exploration has revealed, the ice also hides larger secrets. Beneath its white surface lie the remains of forests that once stretched to the pole, the fossils of creatures that basked in Arctic sunshine, and possibly even the traces of intelligences that looked up at the northern lights from lands that were green with life. These discoveries force us to confront the possibility that the frozen wasteland we consider normal is actually an aberration. Temporary pause in a much longer story of warmth and habitability. The scientific evidence we've examined demonstrates beyond doubt that dramatic climate change is not just possible, but inevitable in Earth's future. The orbital cycles that have driven ice ages and warm periods for millions of years continue to operate, promising future transformations that will reshape the planet regardless of human activities. The question is not whether the Arctic will change again, but when and how rapidly those changes will occur. Yet the gaps in our knowledge remain vast. The rapid transitions evident in ice cores and fossil records suggest that Earth's climate system can shift between stable states much more quickly than gradual astronomical forcing alone would predict. The mechanisms that trigger these rapid changes, and the possibility that human activities might inadvertently activate them, remain among the most important unanswered questions in climate science. The alternative theories we've explored, from pole shifts to hollow Earth concepts, remind us that conventional scientific understanding is constantly evolving. While most fringe theories lack supporting evidence, they serve an important function by identifying gaps in orthodox explanations and encouraging researchers to consider possibilities that might otherwise be overlooked. The history of science is filled with ideas that seemed impossible until they weren't. Perhaps most significantly, our journey has revealed how much of Earth's history remains unknown or poorly understood. The discovery of new species in every Arctic expedition, the unexpected complexity of ancient climate systems, and the ongoing emergence of archaeological anomalies from melting permafrost all demonstrate that our planet still holds secrets that could transform our understanding of life, intelligence, and the possibilities for civilization under environmental conditions radically different from today's. The myths and legends we've examined may preserve cultural memories that extend far beyond written history, encoding information about environmental conditions and human experiences that predate all conventional historical records. If these stories contain kernels of truth about habitable polar regions, they suggest that human civilization has weathered environmental changes far more dramatic than anything in recorded experience. As climate change accelerates the melting of polar ice, we are conducting an inadvertent experiment and accessing these frozen memories. Each year brings new discoveries emerging from permafrost and retreating ice sheets, mammoth carcasses with grass in their stomachs, ancient tools at impossible latitudes, geological formations that challenge conventional explanations. We are witnesses to the unlocking of a planetary archive that has been sealed for millennia. The implications extend far beyond academic curiosity. Understanding how Earth's climate system has behaved in the past provides crucial insights into how it might behave in the future. If the ice sheets that currently regulate global climate can disappear rapidly, as geological evidence suggests, then the stable conditions that have supported human civilization may be far more fragile than we realize. But the Arctic's history also offers hope. Life has not merely survived traumatic climate changes. It has thrived under conditions that seem impossible by today's standards. The tropical forests that once flourished at the North Pole demonstrate that life possesses an extraordinary capacity for adaptation, and that Earth's biosphere can support complexity and beauty under environmental conditions that have no modern parallel. The possibility that intelligence has adapted to and even flourished in extreme environments throughout Earth's history suggests that consciousness and technology may be more resilient and creative than we assume. If advanced civilizations once existed in polar regions, their achievements in adaptation, environmental management, and sustainable technology might offer insights that could help contemporary civilization navigate its own environmental challenges. As we face our own period of rapid environmental change, the Arctic serves as both warning and inspiration. It reminds us that stability is temporary, that change is the fundamental nature of our planet, and that the conditions we consider normal represent just one brief moment in a much longer story of transformation. The ice is melting, and as it retreats, it reveals landscapes that have been hidden for hundreds of thousands of years. Some of these revelations confirm what we expected to find evidence of climate change, preserved ecosystems, and geological processes that operated in the deep past. But others challenge our assumptions and hint at possibilities we haven't yet learned to imagine. In the end, the Arctic ice stands as Earth's greatest memory, preserving in its frozen depths the record of every climate that has ever existed, every form of life that has ever adapted to polar conditions, and possibly even evidence of every intelligence that has ever looked up at the aurora and wondered about its place in the cosmos. The question of whether the North Pole was once habitable has led us through science and speculation, myth and mystery, certainty and doubt. The answer, preserved in ice and waiting to be discovered, may transform not just our understanding of climate change, but our conception of what life and intelligence can achieve under conditions that challenge the very limits of possibility. As the last light of our exploration fades into the endless Arctic twilight, we re-left with the profound realization that we live on a planet whose true history is still being written by every snowflake that falls, every ice sheet that melts, and every discovery that emerges from the frozen memory of Earth itself. If this journey through time and ice has sparked your curiosity about the hidden stories our planet holds in its most remote places, consider joining us for future explorations into the mysteries that lie at the intersection of science, history, and imagination. The Earth remembers everything. We're only just learning how to listen.